Okay, so now on record. We need to start because whoever is not here would have to watch the recording. So before I begin, I want to find out if my voice is audible. Can you guys hear me?
Yes, please.
Okay, that's good. And then the next thing is I need to know if you guys can see my slide. Can you guys see my slide?
Yes, please. You can see.
Okay, that's fine. So we couldn't hold a class last week because it was a Friday and you had your IA, and I think I remember the IA lasted all through the day, and so there was just no space to hold the class. So we had to postpone it to this week. So now we are behind by one topic. But let's move on so that we cover up the grounds we've lost. All right, so the last time we were discussing deductive reasoning, and we saw all the mechanisms of deductive reasoning. And so today we have to look at inductive reasoning. So just like we discussed before, deductive reasoning, as you will recall, is that one in which the relationship between the premises and the conclusion is a logical one. So you saw that just like mathematics, the meanings of the contents don't really matter. But in contrast, inductive reasoning is that one where the relationship between the premises and a conclusion is not logical. There isn't a logical relationship, and because of that, it is possible to affirm all the premises and deny the conclusion without contradiction. Now, that is possible because, like we saw in the last class, the premises are capable of producing more than one conclusion. So because the premises are capable of producing more than one conclusion, it means you need to look at the meanings of the contents. You need to look at the meanings of the contents of the premises and then use your common sense to decide for yourself which conclusion you would prefer. Since it's a probability argument, like we saw in the last class, it means you just have to look beyond the logic. You have to look beyond what the argument is suggesting, because the argument is not really suggesting one conclusion. And then you have to make your own calculations outside the argument to decide which conclusion you would want to adopt. So that's the problem with inductive arguments, and we're going to see it. We're going to see it shortly. Now, for an inductive argument, the premises provide reason for believing in the likelihood of the conclusion. But premises do not guarantee the conclusion, So inductive arguments are probability arguments. They are probability arguments, strictly speaking. And that's because inductive arguments do not depend on rules. They don't depend on rules. So they are a bit harder to evaluate, And from my own experience of teaching inductive arguments, I will tell you, that as my own definition, inductive arguments are arguments that are saddled with more than one possible conclusion. And they're saddled with more than one possible conclusion because the premises support but do not guarantee the stated conclusion. So that's what they boil down to. Now, in order to begin to understand inductive arguments, we need to first make certain clarifications. Now, we'll begin with this clarification between verifiable and confirmable statements. And now, verifiable statements are statements we can directly test or verify. They are usually factual or empirical statements. For example, you would say Kofi lost strength with age. Kofi lost strength with age. That's a factual statement, an empirical statement, and it's verifiable. In contrast, confirmable statements are those ones that we cannot test or verify directly, except through verifiable statements. So, for example, we will say, all men lose strength with age. All men lose strength with age. So that's a confirmable statement. You cannot verify that. You can only examine it by rather examining verifiable statements. So let's look at it this way. If we are to combine both, now this is an argument where you have four premises that are verifiable statements, and then the conclusion is a confirmable statement. Now, so look at the verifiable statements. You have up to 4 men who lost strength with age. Kofi, Peter, Michael, James lost their strength with age. And then the conclusion is that all men lose strength with age. Now you can see that the premises are verifiable statements leading to the conclusion, which is a confirmable statement. Now look at another example. This other example will give you another perspective. Now there are 6 premises here, indicating that 6 different women reached menopause either before the age of 35 or after the age of 35. Now the first premise tells us that Mary reached menopause by 40, and then Grace reached menopause by 35. Meredith reached menopause by 33. And then Rose reached menopause by 34. Edith reached menopause by 38. Sophia reached menopause by 45. And then the conclusion is that half of all women will reach menopause by 35. Now that conclusion is based on the premises. Now this is a typical inductive argument. It's a typical inductive argument. Now let's look at how we can detect confirmable statements. How do you detect confirmable statements? Now, first of all, as you've already seen, confirmable statements are not directly testable or verifiable. They're not directly testable. And secondly, they can be converted into conditional statements. For example, look at the categorical statement. The following categorical statement: no leader steps down from power unless compelled by a coup or constitution. That's a categorical statement. No leader steps down from power unless compelled by a coup or constitution. Now you can convert it to a conditional. Now the conditional translation would be, if X is a leader, then X will not step down unless compelled by a coup or constitution. That would be the conditional version. If X is a leader, then X will not step down unless compelled by a coup or constitution. So that's how to convert categorical to conditional statements. Now, it is impossible to convert directly testable statements into conditional statements. So one of the ways to find out if a statement is a confirmable statement is that it is convertible or translatable into a conditional version. But if a statement is directly testable or verifiable, you cannot convert or translate it into a conditional version. So converting into a conditional version is one of the ways to know if a statement is a confirmable statement. Now let's look at the following. A statement that is directly testable or verifiable can't be converted into a conditional statement or version. Now, Kofi lost strength with age. Now, would you say if a man is called Kofi, then such a man lost strength with age? You see, that's not an appropriate conditional. That's not how conditional statements read, because it would mean that all men called Kofi are old, and there are no children or young people called Kofi, which is not true. And also, there are no strong young people called Kofi. So the statement, you can't convert it because it's not generalizable. It's about a particular person. Because it's about a particular person, you can't convert it into a conditional. Okay, so now we've seen two ways of converting, of identifying confirmable statements. We said confirmable statements are not directly testable or verifiable. And secondly, confirmable statements are the only statements that you can convert into conditional statements. And we just saw how that works. Now, the next thing we're going to do is to remind ourselves of the distinction between finite and infinite reference classes. We did that in our last class. We say the finite class is a class of countable items. Example, this copper, that man, some boys, that table, and so on. So that's a finite reference class. And then we said the infinite reference class is a class of uncountable items. Example, all metals, all men, all voters. So we need this distinction here because it will help us to understand the difference between law-like and statistical hypotheses. Now, law-like hypotheses are confirmable statements that refer to all members of a class. That is, confirmable statements with the infinite reference class. Confirmable statements with the infinite reference class. That is, confirmable statements that refer to all members or no members of the class. They are the law-like, we call them the law-like hypotheses. Example, all metals expand when heated. That's a confirmable statement. And because it refers to all members of a class, we call it a law-like hypothesis. You can convert it to a conditional very easily. The conditional version, if X is a metal, then X will expand when heated. Another example, all Fs are Gs. That means that each F is a G. And then no Fs are Gs means that all Fs are not Gs. So these are all law-like statements. They are law-like statements. They apply to all or none. That's why we call them law-like. When something applies to all, then any member of that thing shares in a compulsory way in the attributes of what has been attributed to all. Now, the law-like hypotheses are highly predictive. Now, G must be attributed or not attributed to every F. We just saw that all Fs are Gs or no Fs are Gs. And we're saying that G must be attributed or not attributed to every F. So that's why we call it law-like. All men are mortal. If Peter is a man, then Peter is mortal. So that's law-like. If Peter is a man, then it's already a law that Peter will be mortal because all men are mortal. Anything that is a man It's very predictably mortal. So we call them law-like hypotheses because they are highly predictive. Now let's look at statistical hypotheses. Now, statistical hypotheses are comparable statements referring to some percentage less than 100 and more than 0%. Example, 90% of those who ate the food fell sick. So that's a statistical hypothesis. Now, look at some statistical terms. Some, few, many, most, hardly any, typically. Now, statistical hypotheses are less predictive. For instance, if X ate the food, X is likely to fall sick. You wouldn't say X fell sick. If it were 100% of those who ate the food fell sick, then you say that if X ate the food, X will fall sick. But in this case, we are told that it is 90% of those who ate the food that fell sick. So if X ate the food, we are not entirely sure that X will fall sick, because X could be among the 10% who did not fall sick. So you can see why statistical hypotheses are not law-like. They don't apply in a law-like way. And that's why we also call them statistical, because they are somewhere between 100% and 0%. So we call them statistical. And of course, you can see they are less predictive compared to the law-like ones. Now, let's move on. So, in general summation, before we proceed, inductive arguments are aimed at confirmation. Deductive arguments are aimed at proof, which we have already seen. Now, confirmation is not proof. Confirmation is not proof. So here we see the suggestion that confirmation is not as strong as proof. The terminology of confirmation is used in your textbook, but some other logicians will not say confirmation. They will say support, that support is not proof. And, of course, inductive arguments provide support for believing their conclusion, but you know that the support that inductive arguments provide is not proof, So support is not always proof. Now, evidence confirms but does not prove the truth of a hypothesis. Evidence confirms but doesn't prove the truth of a hypothesis. Now, so evidence itself has a limitation, which we're going to see right now. Now, before we see that, let's talk about two major ways to detect inductive arguments. Now, so the question is, how do you detect inductive arguments? How do you know that an argument is inductive? So there are two ways. First of all, inductive arguments are capable of more than one conclusion. They are capable of more than one conclusion. For instance, 90% of those who ate the food fell sick. Amma ate the food. So you have two possible conclusions. Yes. You could have Amma fell sick, Amma did not fall sick. Look. Okay, so you can see two possible conclusions. And then the second way of detecting inductive arguments is that inductive arguments are, extrapolations. They are extrapolations. Now, some of you must have heard of the word extrapolation. Okay, so extrapolation. An extrapolation is an activity that smuggles in information into the conclusion that is absent in any of the premises. An activity that smuggles in information into the conclusion that is absent in any of the premises. Now, all inductive conclusions contain information that is not accounted in the premises. That's how you know that an argument is an extrapolation. Now, you remember that for deductive reasoning, when you are looking at a deductive argument, you would see that the conclusion was fabricated entirely from the information in the premises. The conclusion of a deductive argument is just a mathematical construction from whatever you see in the premises. But when you check an inductive argument, you see that the conclusion of an inductive argument will contain something, a piece of information that you can't find in any of the premises. So for inductive arguments, there is always some information in the conclusion that you can't find in the premises. And that means that the conclusion smuggles in some information that is not accounted for by the premises. So that's another way of knowing an inductive argument. That makes an inductive argument an extrapolation. Okay. Now let's look at the technicality of induction and why you have such strange information in the conclusion. Now look at this. A known thing A has certain properties. Something called A has certain properties such as X, Y, and Z. Now another thing B that is not in the premises has the same properties X, Y, and Z. So A has X, Y, Z, B has X, Y, Z, and then A also has some additional property Q. Now, on the basis of the above three premises, the argument concludes, in reality extrapolates, that B also has the additional property Q. So the idea of induction then is that if B is like A in some respects, it may also be like A in other respects. So you can see the word may. It uses the word may, that it may also be like A in other respects. You are not entirely sure. Just because A and B have common properties X, Y, and Z, doesn't mean that if A is found to have another property Q, that B must also have Q. And yeah. Okay, so that's the technicality of induction. Now let's now we have understood the technicality of extrapolation. Now let's look at different directions of extrapolation. Now there are different directions that extrapolation could take. First of all, you have part-whole extrapolations, attributing something to a whole that constitutes a part or parts. Now, so we have two types of part-whole extrapolations. We have generalizations and we have statistical syllogisms. Now, generalization, this is an example. Peter is strong, James is strong, all men are strong. So that's a generalization. Peter is strong, James is strong, all men are strong. And then the other part-whole generalization, or part-whole argument, We'll call them the statistical syllogisms. Most Canadian university students drink alcohol. Caroline is a Canadian university student, therefore Caroline drinks alcohol. So these are part-whole arguments. So the other one is a generalization. It goes from particular to general. This one calculates from the general down to the particular. Okay. Now, we also have analogies. Analogies are another kind of extrapolation. Now, arguing that something possesses the same thing as another because they both possess some other properties. Arguing that something possesses the same thing as another because they both possess some other properties. So that's an analogy. Example, the structural adjustment program was good for Cameroon, which is a third world country. The structural adjustment program was good for Uganda, which is a third world country. The structural adjustment program was good for Senegal. It was also good for Nigeria. Therefore, the structural adjustment program must be good for Togo, which is a third world country. So this argument cites about 5 countries which are all third world countries. Now, so this argument takes off from the fact that these countries are what? Third world countries. And from the fact that these are all third world countries, the argument says that whatever happens in some of these third world countries should also apply to the other third world countries, because they are what? Third world countries. And also the argument extrapolates that just because these countries share a certain quality, just because they share a certain quality, just because these countries share a certain quality or property, they could also, have some other properties in common. That if you notice some other property in one of them, it is possible that the others could have it. So just because they are third world countries, if the SAP worked well in some of them, then then the conclusion will be that the SAP would work well in the other one. So that's an analogy. Now let's look at predictions. Attributing a quality to a future event because of the level of frequency of past occurrences of the same quality in similar events. Attributing a quality to a future event because of the level of frequency of past occurrences of the same quality in similar events. So, for example, we have Tyson has won his last 30 boxing fights. Therefore, Tyson will win his next boxing fight. So, this is a prediction. But of course, as you can see, there is an information in the conclusion that is not in the premise. So that information is an information about a future fight. So the premise does not contain any information about a future fight, but a future fight is being mentioned in the conclusion. So that's why I would say that in inductive arguments, you will always find an information in the conclusion that is not accounted for by the premises. Now, it is possible that Tyson would lose his next boxing fight. So these are the directions of extrapolations. In all examples of extrapolation, you would find something the conclusion talks about that is not accounted for in the premises. Now, having looked at different kinds of extrapolations, which are inductive arguments, Let's look at two kinds of inductive arguments based on strength. Let's look at two kinds of enumerative inductive arguments based on strength. Now, an enumerative argument is an argument with many premises. Sort of enumerating the premises like a list. So the first kind of argument we're going to look at are arguments with law-like hypotheses as conclusion. For example, you have 10 premises here. 10 premises about 10 different metals that expanded when heated. So premise 1, gold expanded when heated. Premise 2, silver expanded when heated, and so on. Bronze expanded, copper expanded, down to premise 10. And then the summary premise tells you that all the metals tested so far expanded when heated. And then the conclusion is that all metals expand when heated. Now you notice that the premises are all about a particular metal. So the premises are working with the finite reference class. They are about particular metals. And even the summary premise is also working with the finite reference class. It's referring to certain particular metals that have been tested. Then you come to the conclusion, and then you notice that the conclusion is rather working with the infinite reference class. The conclusion is working with the infinite reference class. So you can see that the conclusion breaks away from all the premises in terms of the reference class. Whilst the premises are referring to particular metals, the conclusion is referring to all metals. That in itself is an information that is not accounted for in the premises. The premises, both individually and collectively, do not and cannot refer to all metals. But the conclusion is referring to all metals. So all metals, therefore, would be the information in the conclusion that is not accounted for in the premises. So that's why we said that anytime you look at an inductive argument, you find information in the conclusion that is not accounted for in the premises. That's another way of identifying an inductive argument. Now, this particular argument is an argument that ends up with a law-like hypothesis as a conclusion. It has a law-like hypothesis as a conclusion. And frankly speaking, the conclusion is a little bit difficult to defend. It's difficult to defend because it amounts to reaching a conclusion about all metals based on experiments performed with 10 metals. So you are jumping from 10 particular metals to all metals. So there's a jump, a sort of leap, a sort of logical leap. Or you can even say it's an illogical leap. Now, so let's look at the technicality. Premises 1 to 10 are verifiable or particular statements. The summary premise is a summation of all the verifiable premises, and then the conclusion is a confirmable and general statement. So the argument is strictly invalid because it involves jumping from verifiable to confirmable statements. And that's the reason why confirmation is not proof and inductive arguments are not valid. And in fact, that particular conclusion is false because some metals, as it turns out, some metals in fact do not expand when heated. Such metals are called superconductors. They do not absorb heat, therefore they do not expand. So the conclusion is false and all the premises are true. And that's why we say that it is possible to deny the conclusion with all true premises or affirm the premises and deny the conclusion. So it's only in inductive arguments that you can get true premises and a false conclusion. The premises cannot be true, and then the conclusion is false. That's another way of identifying an inductive argument. The premises might be true, and then the conclusion is false. And yet there is no contradiction, because yes, because it's an argument that is capable of producing more than one conclusion. So this is applicable to all the types of extrapolation, whether it's the part-whole arguments, the analogies, the predictions, and so on. Okay, so now we've seen a little bit about inductive arguments that end up with law-like hypotheses as conclusions. Let's look at a few more comparisons between inductive and deductive arguments. So we'll look at that before we move on to the second type of inductive argument. Now, to compare deductive and inductive arguments, let's look at the issue of accuracy versus providing information. Now, deductive arguments are accurate at the expense of the inability to provide information. Now, for example, look at the following deductive statements. Example 1. Either it is raining or it is not raining. That's a disjunctive syllogism. Either it is raining or it's not raining. And then premise 2. If it is raining, then someone will get wet. Now, premise 1, either it's raining or it's not raining. It's an accurate statement. The statement is accurate. It will always be accurate. If it is raining, the statement is accurate. If it is not raining, the statement is still accurate. So this disjunctive statement is accurate for all situations. But does it tell you anything about whether it is raining or not? The answer is no. It doesn't tell you that it is in fact raining. And so you can say that the statement is accurate at the expense of providing you with information about whether it is raining. And then premise 2, if it is raining, then someone will get wet. If it is raining, then someone will get wet. Now, that's a conditional statement. That's a conditional statement. And the statement will always be true because if it's raining, not everyone would avoid the raindrops, or let's say not everyone can avoid the raindrops successfully. So if it is raining, someone will definitely get wet. Now that statement is accurate and it will always be accurate. But does it give you any information about whether it is raining? No, it doesn't tell you whether it is raining. So you can say that it's another statement that is accurate at the expense of providing information about raining. So that's what we mean by accuracy at the expense of providing information. Now let's look at the advantage and disadvantage of inductive arguments. Now, inductive arguments, on the other hand, provide information at the expense of accuracy. Now, the reason for that is that providing information is to be falsifiable. When you provide information, the information you have provided is what we call falsifiable. It can be falsified. Example, it is raining right now. It is raining right now. When someone tells you it is raining right now, it is providing information about whether it is raining. But is it always true? No. If someone tells that to me right now, when it is not raining around me, then it is false. So when you provide information, especially empirical or factual information, such information is what we call falsifiable. It can be falsified. So that's what we mean when we say that inductive arguments provide information at the expense of accuracy. And whenever you provide information, the information you've provided is what we call falsifiable. Now, falsifiability and science. Any valuable empirical information must be falsifiable. Any statement that is not falsifiable cannot be a verifiable or confirmable statement. And any statement that is absolutely true has no empirical content. Any statement that is absolutely true cannot have an empirical content. So only non-empirical statements can attain absolute truth. Empirical information does not have that advantage. Now, the more valuable an empirical information, the more falsifiable it is. So, the empirical statement, it rains every fourth Friday of the month, is more valuable information compared to the statement, it rained just now. Now, if someone tells you it rains every fourth Friday of the month, it can help you to make more arrangements to avoid rains compared to the empirical information, it rained just now. So the value of the information depends on what you can use it to do. You can decide that every fourth Friday of the month, you are not going to step out of your house. So that information, you can calculate the value of that information by how much it helped you to achieve or how many changes it helped you to effect. So the more valuable, the falsifiable. It will take only 1/3 Friday of not raining to falsify the first statement. The statement, it rains every third Friday of the month. So the more valuable a piece of information, the more falsifiable it is. Now let's look at the second type of inductive argument, the arguments with statistical hypotheses as conclusion. Example, premise 1. Michael was vaccinated for polio and never suffered polio. Gilbert was vaccinated for polio and suffered polio. Mary was vaccinated for polio and never suffered polio. Stanley was vaccinated for polio and never suffered polio. James was vaccinated and never suffered. Bob was vaccinated and suffered it. Jill never suffered it. Samuel never suffered. John never suffered. Carol never suffered. So the summary premise, 8 out of 10 people who were vaccinated did not suffer polio. So 2 people suffered after vaccination. 8 people did not suffer after vaccination. So the conclusion is what? Polio vaccination has 80% potential of preventing polio. So that's what we call a statistical argument. You can see that the conclusion is not a law-like hypothesis. the conclusion is a statistical hypothesis. Now, so we have two types of inductive arguments, the ones ending with law-like hypotheses as conclusions and the ones ending with statistical hypotheses as conclusions. Now, hypotheses are technically regarded as conclusions of inductive arguments. So you can see that the conclusions of inductive arguments are technically hypotheses. That's another distinguishing feature of inductive arguments. So at this point, you've already detected up to 4 or 5 ways of detecting inductive arguments. Now, the hypotheses are technically regarded as conclusions of inductive arguments because they are confirmable statements to be supported, confirmed, or denied by verifiable statements. So that's the end of the class. And at this point, I'm hoping you've seen so many ways of detecting inductive arguments. Next week, we're going to look at causal reasoning. Causal reasoning is a type of inductive reasoning. We shall see the nature and advantages of causal arguments. We'll see different patterns of causal reasoning, how we identify causes and effects. So at this point, I think I would need to pause to attend to any questions that anyone might have to ask. So if any of you has any question, he or she can ask so that we attend to it, and then I can start uploading the recording for the benefit of those who couldn't make it. So are there any questions for now? Okay, so if there are no questions, then I'm going to proceed to stop the recording.